Great. My name is Bryn Loftness. I am a doctoral student at UVM in the Complex Systems and Data Science PhD program. And today I'm really excited to be guest speaking for you all to be discussing developing novel techniques for assessment and digital phenotyping of childhood internalizing disorders. More broadly, I'm just going to be discussing today how we use different wearable systems and wearable monitoring systems for identifying things such as stress, depression, and anxiety. With a focus on individuals that are in the age group of about preschool age. So I have the chat up, you'll see, and if you have any questions along the way, I really encourage any questions in real time. So a little about me. Before I ever kind of go into scientific presentations, I always like to give a little bit of background about myself for whoever is listening, just to kind of make it a little bit more personal. So again, my name is Bryn. I am from Minnesota. I did my undergrad in Colorado, and now I love living in Vermont. A few things I really enjoy doing is traveling and doing art. And as you can see, since I was really, really young, I've always really liked computers and what we can do with them and what we can learn from them and with them. So that's kind of just a little bit about me. And I'm really excited to discuss some science with you all today. So kind of the background on what I do within my degree and also more broadly, I work a lot with wearable sensors. That's kind of a broad way of saying anything that is not wired up and that you can kind of move with and go with. You can think of a lot of current wearable sensors that we'll go into later on, but that's kind of my scope. I really like where we're going within this field, and I think more broadly we have a lot of improvements we can make to use these different technologies in more impactful ways, including healthcare, but also monitoring for a lot of different things to make sure that we're having resources go to different communities and etc. You can think of a lot of ways that wearable sensors might be really awesome. Also, specifically what my background is within the scope of wearable sensors, I focus a lot on the engineering and placement of the sensors, but mostly with the algorithm design that we use to parse the signals that are coming from those sensors. And that involves a process called digital phenotyping, which I'll go a little bit into shortly. I also do a bit of work with digital epidemiology, which also uses wearable sensors to kind of monitor close contacts within more of a disease monitoring space. I kind of cross over these fields and find them really similar in that all we're doing is using these tools, these sensors, these signals to find out better ways to improve human health and the overall population. So my current main objectives as a scientist and in my collaborative works is to identify new trends and insights using different digital phenotyping algorithms, which I'll go into shortly if you've never heard of that, using health-related data, whether that's where you are, who you are, how you interact with the world, your behavior, your inherent genetics, and how we can pull that information using wearable devices and health records into new insights that can help improve population growth. I also really like to engage in widespread STEM outreach, such as this live stream. I'm really excited to have been offered the invitation to come speak today. I think getting different groups together to discuss science collaboratively is how we're going to make the biggest growth. So I'm really excited to be here for Proteus TV today. So kind of what digital phenotyping is, let's kind of dig into what I do and what I want everyone to kind of get a better background in during our live stream today. So what a digital phenotype is considered a personalized digital image or a model of your different health metrics, your outcomes, your behaviors. You can think of a lot of different ways that you as a person could be kind of categorized based on, you haven't missed too much. We're just getting kind of started into the deep dive of digital phenotyping. So thinking about digital images and phenotyping, we really want to get a better understanding of how we can represent different individuals and also cluster different individuals better to give them better health insights. And so how that kind of process goes, you can think of it as a very brief four-step process of we want to capture data via those smartphones or wearables, whether it's a Fitbit or it's an Apple Watch, and then kind of take different statistical models to understand what are the biomarkers that we can extract from these signals, whether that, in a more broad sense or more specific sense is your heart rate or how your heart rate is improving over time, however we want to extract kind of the patterns that you're exhibiting. That's what we want to do in that first couple stages. And then the next stage of identifying a digital phenotype is not only to understand for one specific individual how they might be unique or specific, you also want to categorize them into different clusters. And oftentimes, if you have a background in machine learning and you're here today listening to this, you might understand or have background in understanding supervised versus unsupervised machine learning models. And oftentimes, unsupervised machine learning models, as we often do with health data and trying to predict future health outcomes, we don't always have hundreds of health records that are labeled with every single diagnosis or disorder or condition an individual might have. However, you might have some labeled data on that individual, such as, if we go through kind of gold standard diagnosing for specific conditions. And so taking it a step back, we want to start to understand how do people's physiology cluster together into these different groupings, and what can we learn from those clusters of individuals. One specific example is, let's say you have a Fitbit, and then everyone in your surrounding community also has a Fitbit. And Fitbit starts understanding that this subgroup within the community is taking 10,000 plus steps a day, and their heart rate seems to be lower. And then there's another subsection of the community that takes 5,000 steps a day, and their heart rate seems to be a little bit higher when they're sleeping. Let's say that then Fitbit wanted to give kind of some data-driven goal setting advice to that population that takes 5,000 steps a day, saying, if you want to lower your resting heart rate, you should do what this other population is doing. And then you can kind of see how those individuals within that subgroup change based on that biofeedback of understanding, here is your physiology, here's how you can change your physiology, and here's how we're monitoring that growth. And then that kind of goes into kind of step 4 of this digital phenotype of extracting these biomarkers that identify groups of individuals. And then we see if there's similar or different trends among those among the outcomes. So that's a little bit of a background on what digital phenotyping is. It was originally kind of discovered, or I should say coined, by a group at Harvard's Onella lab, which does a lot with stress identification. You can imagine there's good stress and there's bad stress, and then there's whole spectrums in between of that good and bad stress. And identifying what that specific type of stress is and how it impacts different individuals is really what's going to identify and differentiate these different groups and how you give them advice. I'll go a little bit more into what gold standard diagnosing is in just a little bit, specifically with applications of this kid study project I'm going to present today. You can kind of understand and see on the screen how they've kind of derived the digital phenotyping word of what is a phenotype? It's these observable characteristics, eye color, hair color, but how can we get into more of that digital realm of using these wearable sensors, of monitoring behavior or mobility, or how a person interacts with the world and themselves and how their body responds to that. So that's kind of the algorithmic framework that's going to underlie a lot of the research I'm going to present today and hopefully get your feedback and questions on. So kind of jumping back into what are we talking about today? It's definitely a lot of wearable sensors. I think that's the key word that I've said at least 4 or 5 times now. And we do a lot with wearable sensors, and more in our daily lives is it becoming a staple, something we always have all the time. So we've always got our phones on us, usually within an arm's reach. We always have kind of our Google Maps up when we want to, or Apple Maps or Waze or whatever you use to try and get where you need to go. But we also have a lot of different wearables that aren't related to a phone. Those are healthcare devices that we can use. Those are activity trackers like a Fitbit that I've said, but then even recent research in smart glasses and smart earrings and how we can kind of make these different wearable systems that can track signals that are important to us. And there's a lot of growth within this field, not just in the health space. So how we can use these wearable sensors, my specific group here at University of Vermont focuses on how we can use wearable sensors to better identify children with anxiety and depression, more broadly kind of termed as internalizing disorders. Anxiety and depression are 2 types of internalizing disorders. And we've done a lot of research within this field. And how I'm going to talk about the research today is how we've put together all of these different kind of projects that I'll slowly go into, and what we're learning and what we're weaning, and what we really want to understand moving forward. And so if you're ever curious, at kind of the end of this presentation, you can always go back in the recording and look up any of these old citations of our previous work that we've kind of shared into the world thus far. A few of those main things we've done within our previous work is looking at different behavioral tasks, which I'll go into in a little bit. But based on behavioral tasks and kind of creating a new assessment, which is kind of the whole goal, we started to identify features specifically due to physiology and derived from physiology that can help us understand how things are changing in the body and how things are unique to children with depression. So how we kind of do that and why we do that is what I want to talk about now. And a lot of people, when they're first hearing about this project, have a lot of questions, which I can definitely understand if you might have a lot of questions. What are we defining as children? So we focus on kids from about around a preschool age, around 4 to 8 years old, of both genders. And surprisingly, within this range, a lot of individuals don't realize that about 1 in 5 kids, based on previous research, not just within my lab, but all over the world, are showing that kids within this age range are showing early signs of anxiety and depression. About 1 in 5 kids, with about 20% showing anxiety and about 5-ish%, 1 to 5-ish% showing depression. That early on in childhood. And one kind of issue with that age group having these early afflictions is that they can't often speak to those abstract emotions that they're experiencing and ask for help like an adult can or potentially a teenager can. And so it's left up to a lot of other people trying to identify these afflictions in them without them being able to speak forward for them. And so because of this, a lot of children end up untreated. And these conditions have a lot of comorbidities that can cause issues later into life. That includes higher propensity to drug abuse and difficulty networking and difficulty making those long-term connections that they need to, just because early in childhood they were stunted and didn't get the treatment and intervention they needed. And then one thing on top of that is because a child cannot specifically speak to their own abstract emotions and maybe tell their caregiver how they're feeling, especially in current times where maybe a caregiver is a little bit distracted or has to work from home because we have just gone through the last 2 years of a pandemic, and we still kind of progress into this space where it's hard to identify what normal reactions are in children and what might be reactions due to the environment and current circumstances. And current screening for these internalizing disorders is reliant exclusively on these parent report questionnaires. And so a parent will come into a clinical office and they'll have to kind of go through this procedure while they'll fill out a lot of surveys and kind of go through this interview process that I'll go into a little bit later. And it can take quite a long time. And it isn't actually based at all on the child's physiology. And so that's where my group, the Kid Study, kind of comes in. In recent times, we've been seeing, just especially within the past couple months, an increased awareness of childhood and overall span of livelihood mental illness screening for adults, for kids, for teenagers, because there's been that larger focus as of recent in kind of popular culture, which is really great and also gives extra relevance to this study specifically of saying who should be screened for anxiety and how early we should start. And within our study specifically, even though we look at ages ranged 4 to 8, we do see that the higher propensity of them being affected with an internalizing disorder is, towards that 7 to 8 range, 6 to 8 range. And it is definitely, I see in the chat, it's hard to imagine a child that's 8 years old with anxiety. But surprisingly, it's, harder to see and imagine. But once you start kind of going through these clinical visits and doing the research, you see that more and more is this becoming a problem that's coming into the public space. And so as I've kind of talked a little bit about the current systems in place, the gold standard assessment is, like I said, that clinical interview that can take about 2 hours in addition to surveys. And I won't kind of go into the details of those. There's a few different kind of gold standard ways that have been kind of tested by different psychologists and clinical psychiatrists throughout the years that are really used. The problem is they require experts within the field. You can't just go to a pediatrician's office and say, my child is experiencing, something that seems a little off, or they're behaving in ways that I'm not sure is normal for their age, or if they're feeling, up to what the other kids are feeling up to doing. And one big problem here in Chittenden County, where UVM is placed, there's currently a 9-month wait list just to get in on the initial interview for this screening process. And that's kind of prevalent across the United States, and even outside of the United States, of a limited access to this expertise to go through these screening processes. And so that kind of begs kind of innovation within this space of how can we create better screening tools. Another problem with this gold standard assessment, as I've briefly mentioned, is there's reporter bias. With not using the actual child's physiology or how they feel directly from them, and just using an observer to kind of speak to what they're seeing, what they're observing, how they compare to other kids around them, that can cause for a lot of underreporting as well as overreporting, which we see within our study a lot when we have them go through the gold standard assessment in addition to our new assessment we're designing. So that's kind of a huge problem, is we have these kids, and even when we get them in for these interventions, we're missing a lot of them just because we don't have the best view on what they're experiencing and how their disorder is presenting. We also don't quite capture everyone we want to capture because it's so hard to get into these screening and intervention visits with different individuals that have the expertise they need. And so one big goal that I'll go into later on is making sure that this is accessible for a wide variety of individuals, to make sure that we're casting a wide net and that we are not overlooking as many children that might be experiencing these really tough emotions early on in life. So kind of moving forward, we've created this kind of standard of how we want to validate our new procedure that I'll go into. And we've kind of named it as absorb. If we want our intervention, our new assessment to be absorbed, we know it needs to be accessible. We need to be able to reach several communities. We need to make sure that they're not waiting 9 months for their initial interview. And we also need to make sure that we have a lot of verified results that are, looking at these gold standard assessments. We have a large population size, which is really hard for such a niche population of individuals. We need to over-select for kids that have anxiety or depression so that we can get a proper understanding of what their physiology looks like to create these models. And so we really need it to be believable if it's going to be adopted. We also need it to be scalable. So not only do we need to have individuals able to have it, we need to be able to make it available across, different regions and have the models still function in those regions. And one big kind of component of that to consider is one part of our assessment that I'll break down later on is that we do take in audio data of the child. And so if we train a model on audio from one specific region, we can't always extrapolate that to audio of children in different regions or of different languages. And so making sure that we can create scalable models is really important to us. We also want it to be objective. One of the biggest concerns with it is that underreporting and overreporting when the child does eventually get in for that parent report screening. And so we want it to definitely be able to be based on physiology using wearable sensors. And then the last two is it needs to be repeatable. We need to have consistent results, and it's got to be brief. We can't have parents have to come in, wait 9 months, and do a 2.5-hour screening out of their day when it's already really hard to get in the first place and take time off. It's just not feasible, and it doesn't cast a wide enough net to make sure that we're conveniently catching as many kids as we possibly can. And so moving forward based on that criteria, we've kind of set forward a set of aims that we've been working towards for the last several years, specifically a lot in this past year, of we want to use this platform, these validation steps to create this innovative, data-driven, physiology-based marker identification system for kids with internalizing disorders. And so using wearable sensors, what identifies a child that has a disorder or is maybe borderline to potentially having a disorder later in life, and how can we identify that just through physiology? And then we also want to use that information after we identify those biomarkers of creating this new assessment procedure that isn't going to diagnose kids, but it can be done in, pediatrician settings where you don't have to wait 9 months for an expert. And we'll tell a pediatrician, okay, we should then refer this individual higher up in the list or sooner up in the list. It's kind of a triage system to better identify kids in a wider scope. So based on those aims, here's some photos of some sensors that we use within our study called the biostamp sensors. We collect a lot of multimodal signals from several sensors. We collect accelerometer, gyroscope, and that's kind of capturing the motion of the child going through our different assessment. We also capture speech, which is audio through some of our tasks. We capture kind of muscle tenseness and muscle changes through EMG sensors. We also capture changes in surface potential and kind of sweat production through EDA, electrodermal kind of assessments through those kind of sensors, which are kind of lesser known sensors, but are becoming more prevalent within this space for stress and internalizing disorder identification. We also have ECG sensors to capture what that change in heart rate is, which is really, really important. As you know, like let's say you're about to give a speech in a class. What happens to your body? Oftentimes your muscles tense up, maybe your palms get a little sweaty, especially today when it's so warm outside, maybe you'll get extra sweaty, and your heart begins to race. And so these are kind of the signals that we really want to look at, as well as how are they moving differently. And then using these different signals, let's extract what we find and let's start finding what's the difference? How can we identify what the difference is? Is the difference consistent among different demographics within this age population? So moving forward, I've briefly kind of brought up the behavioral tasks that we use these sensors within. And so I'll go on to them and describe them a little bit now. So when a child comes in, we kind of outfit them with a lot of sensors. A lot of times the kids are really excited because it's like, wow, look, I can see my heart rate on the little screen and I can, have this really cool watch. And we bring them in and we take some baseline assessments with those sensors just to understand, as anytime you use a wearable sensor, you want to understand what's happening in just stillness. What is the child's potential baseline? And then we go through different tasks. The first being the approach task. This represents a potential threat where a child walks into a room and they're presented with it's dark, it's dim, and there's something across the room, and the facilitator that's helping with the study, oftentimes our research assistant, is saying, okay, there's something across the room and we don't want to wake the child. Not the child, the whatever is waiting across the room. And so the child is then intimidated. They're wondering, what's across the room? It's dimly lit in here. And then the facilitator will lead them across the room towards this potential threat. It's just usually a tissue box under a blanket, but this is supposed to kind of represent that apprehension that a child might feel walking into a potential threat scenario. And that's a 30-second kind of task. Next, and in between each of these tasks, we also have rest periods for the child to kind of go back to that baseline and to rest a little bit so that we can get the physiology from each of these specific domains without trying to have too much crossover between the task reactions. Next, we go into the speech task. This is based on 3 minutes, and we just ask the child, give us a 3-minute speech. We're not going to speak, and someone will be judging your speech. And after, of course, the speech task, we let them know no one is judging their speech and that they did a really great job. But this represents an acute threat, just like when you have to give a speech in class. You're going to get a little bit intimidated, especially if it's a 3-minute long speech right off the whim. Next, we have a reward response stimulation task. So we then just allow the child, we turn on a little bubble machine, and for 3 minutes, they can play freely with bubbles. And that's really exciting. I've played with a lot of bubbles with a lot of kids now, and I think through this study, it's easy to get kind of bogged down with it's a little bit dark, and it's tough to think about kids 8 years old experiencing these really tough emotions. But one thing that's fun is you still get to have these cool experiences through this research study of playing with bubbles and popping a lot of bubbles. Next, we go on to the reward anticipation task where we say, okay, you've done so good today, and we're going to give you a toy or a treat. And then about 1 minute pass and we kind of are rummaging around in our toy bin. And then after a minute, we then present the child with a toy. And they're anticipating this toy for the entire 1 minute. And that's kind of a brief overview of the task that we have the child do. This is what the child is doing while the parent is going through the typical gold standard assessment process. And for each of these tasks, as you might remember from me just saying it a few moments ago, each of them range from 30 seconds to approximately 3 minutes. And so the whole assessment array lasts approximately 10 minutes, not counting the rest periods between the tasks. And so that's kind of the big difference between the gold standard and what we're trying to test here is, can we in 10 minutes identify the differences in a child's physiology that is taking also the parent at the same time 2.5 hours to potentially identify with additional bias. And so moving forward, here's a few images of those sensors that I was talking about just briefly before. We collect via smartphone around the kind of waist belt you can see on the screen. We attach that phone to the waist belt and have it on their sacrum, which is their lower back, and that collects audio data as well as movement data. We also use biostamps to collect that muscle change and muscle tension data, as well as the ECG sensor data. We also use that E4, which is the watch. You can see that's the one the kids are always pretty excited about wearing. And that collects information on their surface potential changes with, the sweat production, as well as surface temperature and their heart rate and their movement in their wrist. And so you can see from a lot of different points on the body, we're collecting a lot of different wearable sensor data. And so through this, we want to identify, what are the minimum sensor signals we need. In a pediatrician's office, we don't want to have them have to use 10 sensors on the child. We want to identify exactly where in our point of care diagnostic system, what tasks you need, what sensors you need, and what are the signal requirements in terms of length for identifying those differences. And then using that to create an open source software package that we can use in research settings, and then eventually in more of a wide scale, free living world environment of casting that wider net. In terms of the question in the chat about the privacy concerns, there's definitely some privacy concerns to consider in terms of collecting audio data. I'll later talk about next steps within this project, but we are releasing kind of our algorithm for how different research groups can do the same study. However, obviously, audio data is personal health information, it's voice. And so you have to be very careful and go through a lot of IRB processes to make sure you can collect this data. And the phone is a phone that's used only for the research study. And so that's kind of the main thing. It's also never connected up to Wi-Fi. We always hardwire all of our kind of data processes. And in terms of the IRB processes, you have to, in depth, if you've ever been a part of a research project, or maybe you haven't, which is totally cool. You have to kind of outline everything that you're going to do in the study, everything that might cost money, or how you're going to advertise, or how you're going to recruit. And then you also, throughout the study, have to update the IRB, the internal review board, or I think that's what it's called, the IRB process, and group for what's happening within the study, if there's ever been any deviations from protocol that you've outlined in the study after the study is approved. And so, especially in contexts like this, where you're collecting personal health data on a vulnerable population, such as children, you need to make sure that you're kind of going through the right routes and only getting the information that you really need. So the benefits for participants of doing this study with us, we give obviously the toy to the child in the end. We let them keep that. We also incentivize the family by offering a monetary reward for participating. In addition to, if you remember me saying, there's a 9-month wait list for only the interview initial process for a parent coming in wanting to ask questions about their kid and going through the screening process. If the parent signs up for this study, we give them that gold standard assessment through our own clinical psychiatrist that's trained in all of those screening and gold standard protocol, and are able to provide results to them within 2 weeks rather than 9 months. And then we're also able to collect the physiological data, which oftentimes they're really excited about too, because we select a lot of individuals from that 9-month wait list and ask them if they want to join our study. And so that's a few of the benefits to kind of being a part of the study. And we've had really good experiences with recruitment thus far. And so let's start kind of going into data. And this is where, if you guys have questions in the chat, I'd love to kind of hear what your thoughts are. So this is just an example of a subsection of about 37 kids from our study. We're in the process of collecting data on 100 kids with hopefully a range of about 1/3 of them being affected. We try and over-select for that affected population so that we have enough to train models off of and understand true statistical differences in a variety of demographics. And so this is kind of two charts for a subsection of 37 kids where we're looking at just gyroscope signals at the sacrum. And instead of looking at 3-axis, we're looking at a magnitude, which is just kind of a summarized version. I'm not going to really go deep into the metrics today of how we're driving these signals, but it's a very simple way of summarizing the 3-axis gyroscope movement, which is kind of angular movement. This is going to capture, let's say, if a child is spinning or twirling or jumping up and down or running across the room and having angular movement in their sacrum. And this is just during the joy mood induction task, which, if you remember, is my favorite, the one with the bubbles. And so here we can just look at how is, just visually looking at the data, which is always kind of a fun part of exploratory data analysis. How do we see that potentially affected children and unaffected children, as you'll see from the red being affected children and blue being unaffected children, how might we visually see differences within their data? And this will help us kind of chunk up tasks and also get an understanding of where we might want to start with our feature selection process. And so this is something we did just a couple weeks ago. We've been starting to really deep dive into each of our tasks to build this aggregate model that we're trying to test against. You might see here, we saw that there was, it seemed like a lot of movement at the beginning and towards the end and towards the center for the affected kids, where for the unaffected kids, things seemed a little bit more consistent. And obviously, when you visually look at data, you don't immediately draw conclusions, but it does give you a pointer of where you might want to look next. And so what we did to look next is kind of statically chunk this 180-second bubbles task, which is the 3 minutes, into these 15-second chunks, and then took a lot of statistical measures on those chunks of, gyro data, accelerometer data that we're looking at specifically just from one sensor. And so what I'm giving you now is just a very, very small spoonful of what we're starting to look at in terms of all of our different sensors. And looking at these 15-second chunks and looking at, let's say the sum of the gyro movement within that 15-second chunk, we then can understand what is the total angular movement that child is having in that 15-second time frame. And what's really interesting about looking in those kind of time frames, obviously before you ever go into creating a model, you want to understand how different features might be correlating together. 1, to identify feature redundancy, but also 2, to identify where features might be correlating well to your output and target feature, such as you'll see at the bottom here, the KSADs and the CBCL are 2 parts of that gold standard assessment. And so looking at the CBCL and KSADs, we can see here, looking at feature correlations of all the other features to the KSADs, you'll see 100% correlation in the KSAD column, and that's because we're comparing KSADs to KSADs, that exact feature. But all of these other features that I'm showing here are correlating to KSADs with a certain correlation coefficient, and this is using Spearman to look at monotonic correlations. It's not always going to be linearly scaling together. And one thing that we thought was really interesting in this EDA a couple weeks ago is if you look at the 3rd from the bottom and the 4th from the bottom features and their comparison and correlations to the KSADs. And you can see of these two, I don't know if you can see my pointer, but if you can, it's the 3rd and 4th from the bottom. If you can see, everything but the bottom 3 are movement features that we've derived. You can see kind of medians, sums, 25 percentiles, variances, 95 percentiles. But that 3rd and 4th from the bottom, that CBCL int high, that's a diagnostic result. You can't read the terms on the vertical axis. Oh, that's totally okay. And so if you can't read the terms on the vertical axis, it's basically we're looking at the median bubbles gyro, which is just saying what is the average angular movement in this specific time chunk. And it says 15 to 30, which is the second 15-second chunk within the bubbles task. And this information is not super important in that this feature exists. What's interesting is the similarity and correlations between that movement feature to the next feature down in the list, the 3rd from the bottom of the CBCL int high. That's a diagnostic feature. And so looking at similar correlations between what an output diagnostic feature is from our gold standard assessment, and then also only 15 seconds of data of movement having similar correlations, this doesn't mean that, looking at this 15-second range, we can identify every affected kid or unaffected kid. This just means that we should focus on that range in the beginning of the task of that second 15 seconds where, something is happening in that time frame that's highly correlated not only to one of our diagnostic features, but to others of our diagnostic features of different survey types. And that gives us a lot of, intrigue and interest in why are we seeing such interesting movement? And it's really cool to see such interesting and similar correlations from these different movements of 15-second chunks to a report that's 2.5 hours long and is recording the last 6 months. And that really shows a lot of validity within the study of looking at physiological movement data and physiological response data and comparing that and using that more as a benchmark for identifying potential kids for internalizing disorders versus not, instead of potentially going through an inaccessible route or in addition to going through that more inaccessible route. So that's just to give you kind of a sneak peek. Other things that are really interesting, just to kind of get food for thought. If we're looking still at that bubbles task, you might question to yourself, where in a 3-minute time span of a child playing with bubbles, where might we see in their movement data differences between an affected child and an unaffected child? And I encourage you to kind of think for that for yourself. Do you think it'd be towards the middle where maybe they're getting bored? Maybe it's towards the end when they still want to play, or maybe the child who has anxiety or depression doesn't want to play. Or maybe it's in that first 30 seconds where they're just having that excitement of playing with the bubbles for the first time and they get really pumped about that. So you can see from this chart here, we start looking, a couple weeks ago, I created kind of a feature ensemble comparison method where I'm just looking at a lot of different feature importance algorithms on, these different features we derived from the 15 seconds chunks I showed you earlier, and how do different algorithms that aren't based on a model and aren't based on a predictive kind of system, just feature correlations and feature importance based on different things and different, metrics. How do those rank together, and where temporally are those features repeatedly showing up? So of kind of four different feature significance tests, you can see it's like a ratio on our y-axis there. We see that a lot of, in the CBCL and KSADs, again, you saw those on the previous slide, but basically those are just two parts of our gold standard assessment. And we usually look at them different, but also together in tandem because they sometimes provide different information on the diagnosed child. And so looking at both of those and the two different colors, you can see temporally in this chart of kind of the wave that the beginning of the task in the first 30 seconds or so, and definitely understandable if you can't read that x-axis, that's not really important right now. It's just seeing kind of how the different features are showing in time. And you see in the beginning, that first 30 seconds, a lot of features seem to be really important for the difference between a child that's affected versus non-affected. And then you also see towards the end, there seems to be another kind of jump in feature importance, where during the center kind of 2 minutes of the task, there's not a lot of features that seem to be very statistically significantly important across our different feature significance tests we're doing. And we always do these kind of feature significance tests before creating a model. One, because we're still in recruitment stages. We just reached approximately 50 kids last week. And we still want to get to around 100 before we kind of start doing some transfer learning and kind of have enough kids that we can properly create models. But before we do that, we still need to understand, where do we want to start extracting features? Where in our tasks are individuals kids that are affected might be acting differently, so that we can make sure that we're ready for those modeling stages and have our model be really interpretable and understandable. And so understanding that the beginning and end of the task might be giving us specific insights. This can represent the apprehension or excitement and satiation that affected or unaffected kids might be having. And you can hypothesize many things about that, but I won't go into all of that today as much. So kind of moving forward, The current project status, as I said, last week we got to about 50 kids, which is really exciting. As I said in the beginning of this presentation, we had a lot of different mini studies prior to this work that was on each task specifically in isolation or was on a smaller subsection of data. And so this is quite a large study in terms of this pretty niche population that's pretty hard to recruit. Having 100 kids for this study is going to be very impactful. And we're really excited about that. So that's kind of where we are in the project status. We also have kind of been doing these preliminary case studies and feasibility studies, and we'll be kind of presenting those at various conferences this summer and within the next coming year as we begin to understand more interesting differences in, the physiological responses of kids using these wearable sensors that we're able to start understanding. We're also planning on, as I've said previously in the presentation, one of our biggest aims is to provide this software available and accessibly to different communities and to make this assessment procedure for providing early intervention more accessible. And so we're soon kind of publicly releasing our system for different clinical research groups. Obviously, it's not for the public to test their own kids. This is for experienced researchers and for clinical psychiatrists to also test what they're seeing. And so we're kind of creating this package, this system that's going to include kind of interactive code elements that they can run their data through once they start collecting wearable health data on this population, step-by-step guides on, let's say they want to use the smartphone sensor around the waist and they find a lot of significance there. We've got a protocol for how they can make that wearable sensor and wearable waistband with step-by-step of what they need to buy, what they need to do. And so you can see kind of the goal here, not only in having this system accessible for kids, but it's also for the implementation accessibility as well. So that's kind of where we are in our current status, and also with future work of like, how can we create the system to be exactly what we want it to be and meet these goals that we want to reach, but also the general population wants to reach as well with the increased awareness for mental health across different age groups, and specifically for kids and young adults. And so I ended right where I was kind of hoping to today in terms of having about 15 minutes left for any questions. I'm happy to kind of go back to any slides. I wanted to keep things pretty surface level today in terms of just introducing this realm of research, introducing some early findings of where you can use this movement data, this physiological data in children with wearable sensors to understand how we can make better diagnosing assessment procedures for niche populations. And I presented different things about what digital phenotyping is and how that might be important. If anyone has any questions, I'd love to take them in the chat. And you can also reach out to me and get kind of constant updates about this research and other research that I participate in via Twitter and Instagram on @technologybryn. I love to make it a really open and collaborative scientific effort, all the things we do within the mental health monitoring and wearable health space, which is really exciting. And if you ever have any questions or want to collaborate or get involved, please do reach out. So I see kind of the first question is, how can we extend this technology to countries where the diagnosis tech may be expensive? And that's a really, really great question. One thing to note here is we're using a variety of sensors in this study, some that do cost, a pretty great amount of money. But we also try and use sensors that don't cost as much money, such as that smartphone sensor that goes around the waistband. That smartphone is a Google Pixel, which often goes for a couple $100 versus a wearable sensor system like those biostamps that I showed you that capture the muscle movement data, muscle tension data. Those costs well into the thousands for kind of the whole setup. And so making sure that whatever signals that we find significant, that we can try and find low cost versions of those sensors or show the importance of why having these high cost sensors are the ones that we really need. So that's a really great question in terms of how to make sure that we're making an assessment procedure that is accessible, not only in terms of having the access to experts, but also access to technology in these predictive models. Yeah, does anyone else have any questions? I really hope that you learned a lot, and that if you have questions within the mental health screening space, especially with children, that you look back into, if I just scroll back, into kind of our different previous research in this space, and also kind of stay tuned for when we release our larger system. The more people that have conversations about this field and about this need, the more we'll bring awareness to children who may be overlooked and may be struggling, and not only children but all populations, because as soon as you start the conversation, that conversation can extend. Yeah, so I'll stay on for a couple more minutes, but I really appreciate you all coming and listening. And again, if you're not here live and you have any questions, do feel free to reach out to me at Technology Bryn. Thank you so much for listening here today.